All right, I think we're about ready. So hello, my name's Diane. I'm the maintainer of Massive.js, which is a data access framework for Node and PostgreSQL. It's a little bit unusual in a few respects. First, in that it's working with relational databases in Node, which is already heavily focused on NoSQL stores for the most part, like document DBs especially. Second, that it's more in the data mapper style as opposed to the more common object-relational mapper. And finally, that it's exclusive to Postgres. It doesn't work with any other type of relational database, which is just about unheard of. So what I'm going to be talking about today is kind of the theory or the philosophy of why Massive is designed the way it is, why it, or how it works with data differently from some of its counterparts and other data access libraries, and why exclusivity to Postgres makes sense in Node specifically as opposed to other contexts. I'm also going to get into some of the practical aspects of how Massive represents the database in client code and survey some of the tools that it provides for working with the contents of your data store. Data access in JavaScript would have been a punchline not 10 years ago, and honestly, JavaScript itself still is in some quarters. I'm a little bit guilty of that myself. My background is all in Java and C# back in the old days. But about 5 years ago, I was stuck on a legacy enterprise Grails application, and the boss said, there's a new project coming down the pipeline, but we're using Node. So he could have told me it involved COBOL, but I learned JavaScript. That was how. And what I found when I started digging into it was Doug Crockford calls it the world's most misunderstood programming language, and by and large, he's correct. You've got first-class functions, so you can be all cool and functional. You've got a prototypal inheritance model as opposed to the more common class-based version. There's the complete lack of type safety, which is scary enough that there are multiple static type checkers in the form of TypeScript and Flow. And all of these aspects are kind of weird at first, but they're all critical to how Massive can actually work. The real elephant in the room, though, if you will, is the exclusivity to Postgres. So like I said, using a relational database with Node is already a little bit unusual. People generally reach for MongoDB first or maybe Couch, but that's largely because you can speak JavaScript to the database, and you work in terms of JSON documents, which are very easy to work with in JavaScript. But the thing that we've discovered in the past few years, is the whole NoSQL backlash sort of got off the ground, is that all of these NoSQL stores are specialized. You have the document databases, key value stores like Redis, and big table derivatives like Cassandra or HBase that are all extremely good at a certain set of things, and they're not generalists. Relational databases, meanwhile, have been sort of the Swiss Army knife of data access for the past 45 years. They can do just about everything tolerably well at sub-planet scale. And unless somebody manages to turn the entire field of discrete math on its head, they're going to be doing that for the next 45 years as well. So they're here to stay. But when you do use a relational data access framework, you expect to be able to transplant, to build it on MySQL, deploy it on SQL Server, or both. And a lot of data access libraries tout compatibility as a selling point. The idea is that it shouldn't matter which DBMS or database management system you're actually using, except it kind of does. So every DBMS has a different approach to conformance with the standard. It's issued every few years by the American National Standards Institute, and it describes the ideal relational database. If ever actually implemented to completion, whatever product managed to do it would fetch your slippers and make you breakfast in bed. It's extensive, and there's a lot in there that nobody's really gotten into. So every actual database management system is sort of catching up to what's in the standard, and as the new version comes out, they get further and further behind. Some DBMSs actually just go ahead and violate the standard anyway. Probably the easiest example is SQL Server with top. The standard specifies that you limit the number of results by using the limit keyword at the end of a query. SQL Server just goes and does its own thing. Out of the major relational databases in existence, the closest one that's kind of difficult to quantify is probably Oracle. Postgres is the next best, and it's also about the only one that any of us could afford on our own, because it's free. Postgres notably managed to get out ahead of the standard in 2016 when ANSI introduced the JSON section of the standard. Postgres actually already supported it, and had fairly robust set of tools for working with JSON inside relational tables. It has a whole host of other features too that appear in only some or none of its competitors. You have array fields, you have table inheritance, materialized views, common table expressions. Probably the most important from an architectural perspective is the foreign data wrapper, which allows you to represent a MongoDB collection or a spreadsheet or a REST API, basically anything that represents information in discrete records as a table, which you can then retrieve information from and write information back to. So another reason to be sort of going long on Postgres is that it's kind of having a moment. The y-axis here is logarithmic, so bear that in mind. But the RDBMS world has historically been dominated by sort of the big three, MySQL, SQL Server, and Oracle. Postgres is beginning to make inroads on turning that into the big four. It actually did pass MongoDB on this chart to become number 4 overall, not just in relational databases, early in 2017. But there's one really important characteristic that Postgres has besides just having all those features and being kind of an underdog on the rise, which is that it is the only major RDBMS that is really community-driven. After Oracle bought MySQL and Monty Woodenius broke off to start MariaDB, none of the big three are truly community-backed projects anymore. SQL Server and Oracle are both proprietary. MySQL is joined at the hip to Oracle. Postgres, meanwhile, has been around since 1996, so it's a very stable, very mature product. And if you want enterprise support, you can get it from Citus or EnterpriseDB or any of a host of other vendors. But it being a community project is also something of a weakness, because without that community that's actually writing code for it and around it, it's dead. There's just nothing there. So I think it's really important to keep the open source option viable, and that means writing code that targets it not just explicitly, but exclusively. So after the choice of language and database, probably the biggest question in back-end architecture for an application is how do you approach data work itself? And the object-relational mapper, or ORM, is a very common choice for that. And there are really reasons it's attractive. You don't have to write SQL to get started, which, if you don't already know SQL, is kind of intimidating. You don't have to think about the layout of your database, which, again, if it's not a subject you're familiar with, it's a lot to take in. But it's got problems. So this is from a 2006 blog post, and Ted Neward continues that it represents a quagmire which starts well, gets more complicated as time passes, and before long entraps its users in a commitment that has no clear demarcation point, no clear win conditions, and no clear exit strategy. ORMs have major limitations that are not immediately obvious, and they just, as software, encourage a host of bad habits in developers who use them. Foundational to most of these problems is that they encourage a view of the database as a black box that you don't really understand. You just put information into it and pull information back out of it. This contrasts with a view of the database as an organizing principle. This building is the Villa Savoye. It's actually a house built in the late 1920s, early 30s by the French architect Le Corbusier, whose sort of maxim was that a house is a machine for living. So with the Villa Savoye, he had essentially free rein to indulge his principles and make the best case he could for his view of architecture. And it turns out it's actually not that great as a house. You might notice there's no gutters on it, which meant that it's been plagued by rain damage problems ever since construction was completed. And nobody actually lives inside it anymore. It's a museum. And the reasoning behind this is that people really hate living in machines. It's the sort of thing that we write dystopian fiction about. Going all the way back to Theo von Harbu's Metropolis, more famous as the movie, which features machines for living and machines for working. And central to the conflict of that book is one of the machines for working, which is named Moloch, and it eats people, which kind of sets the tone for the whole thing. But when we're storing information, that has to be a mechanical process. we have to have well-defined schemas and relationships, and we have to approach them consistently in order for them to be at all useful. Databases have to be internally coherent, but when you're using an object-relational mapper, it encourages you not to think about that, to put minimal thought into how your information is actually structured when it's being stored. So this results in a whole host of issues that tend to bite people later on in maintenance or post-release, such as poor performance due to inefficient structuring of data, redundancy and inconsistency, having related information stored so far apart it has to be duplicated, organic model growth. If you bake version 1, come back to add a new feature and realize you have suddenly a choice between major surgery on your data model or just bolting something onto the side and hoping nobody looks too closely at it. Many of these issues can be worked around with proper application of SQL, but ORMs were supposed to save you from having to do that in the first place. And if you have some of the structural problems, there's no getting around them, even with a full rewrite of the application. You have to overhaul your database and hope and pray that you can get the information you already have into the new format without losing too much of it. All of this sort of at root comes down to what's called the object-relational impedance mismatch. Both of these models actually represent the same structure, but they look vastly different. So relational databases care about two things: records and links between records. It's like Boolean logic in that the simplicity makes it really, really powerful. Meanwhile, objects in application code relate in many, many more complicated ways in terms of ownership and traversal and all manner of data structures that relational databases don't have a clue about. And it's actually worse in JavaScript because of how easy it is to mutate objects, to add new properties, to change prototypes, do this, that, and the other. So you have to handle the translation from the object model to the data model and vice versa extremely intelligently in order to do it safely. And if you use an ORM for long enough, you eventually have to pay for the convenience that it gave you early on. Basically, anything complicated is going to involve writing SQL. And again, you're supposed to not have to do that. But if you want to actually take advantage of the compatibility selling point, you're writing lowest common denominator SQL. You're ignoring the feature set of whatever database you've settled on in favor of just whatever can be applied across the board. Alternatively, you can split the query logic and have to maintain twice as many queries. If you want to do CQRS, command query responsibility segregation, you're now maintaining 3 data models, not just the actual storage model, but also the application read and the application write pictures of what your data looks like. If you want to do bulk persistence operations, sometimes that's supported to a certain extent, but even when it is present in the library, it's a departure from the metaphor, which encourages you to pull out information and then have each record object manage its own state internally. So this all kind of brings us to the crux of the matter, which is abstraction. So all of software development is about building up layers of abstractions under ourselves. In the early days, we built assemblers to abstract over electrical pulses. Later on, we started designing languages and building compilers, linkers, and interpreters to abstract over assembly with its mnemonics and registers, which were still a bit much to manage. In the 21st century, we've been creating frameworks so that we don't have to think about the low-level plumbing any more than we have to. And there's a temptation to think of the database as that low-level plumbing. It used to be the province of the database administrators, and you had to climb Mount Everest to talk to them and beg for permission to make a change and be told no. But the role of the database has really evolved into a single application persistence store. And that means that application developers have become responsible for design and layout and tuning, even if the day-to-day care and feeding and backup management and that sort of thing is ops department. So we are responsible for what the database looks like, whether we like it or not. So we need to think about how we approach it and the abstract tools that we use to manipulate information. So this is from Towards a New Model of Abstraction in Software Engineering. It's a 1992 paper building on earlier work by Mary Shaw and William Wolff. And Kixalis continues that these abstractions are backed by real pieces of code running on real machines, consuming real energy and taking up real space. To attempt to completely ignore the underlying implementation is like trying to completely ignore the laws of physics. It may be tempting, but it won't get us very far. And the lesson I take from this is that at some point the chips are down and we have real information in a real data store somewhere, and we need to work out how to treat it most effectively for the context that we're actually working in. This is one context. It's my favorite joke in software development, enterprise FizzBuzz. It's on GitHub. Fantastic waste of time, highly recommended. But what makes jokes like these funny is a kernel of truth underneath it all. And here, that underlying truth is that these hyper-verbose abstractions that are really just torturous are how you achieve flexibility in statically typed object-oriented languages. Java recognizes that flexibility is dangerous, and frankly, it's correct. But in order to actually be able to use flexibility or to achieve flexibility in Java, it makes you prove that you understand that too, that you know what you're doing, that you can be trusted with those tools. So it favors formality and precision over openness to just doing whatever you want, unlike other contexts. And okay, there's really nothing true about this one at all, but if you view it through the lens of classical irony, we can see that as developers using dynamic languages like JavaScript, we're a little bit spoiled, to the point that we start to conflate the abstractions that we traffic in, which are really down to the natural expressiveness of the language itself, having first-order functions, having map and reduce as native array methods in the standard library, working on a single thread with asynchronous I/O. We start to think of those as being synonymous with low-level power, and it's really not. Nobody's flipping ones and zeros on a platter using Node. But that's on a technical level. On a conceptual level, these are very fundamental operations that we're performing very, very intuitively. So it kind of is fundamental in that respect, even if this is still a complete and utter crock. So given the differences between the potential contexts that we work in, we need to pay attention to what we're actually working with. So object-relational mappers grew out of object-oriented languages, not surprisingly. The great-granddaddy, of course, was Hibernate, which came out of Java. And they provide a usable metaphor for data access in those strongly typed, formally object-oriented languages. But that doesn't make them the best universal tool. It's like document databases are great at storing hierarchical information, but less good at any kind of general case. So we need to remember that abstraction for its own sake doesn't actually get us anywhere. If we blindly deploy an abstraction that was built and intended for a different context, there's a really good chance that it's only going to make our lives harder. Dynamic languages, specifically, make it really easy to specialize. We don't have a lot of the overhead that languages on the other side of the fence kind of do. We don't have interfaces or abstract classes to worry about. We don't have types. We don't really have access modifiers. There's an asterisk by that one. We don't even have index out of range errors because you just get undefined if you pass an invalid index. So this all encourages us to build concrete systems or specialized systems that still have a very light footprint, because the toolkit the language gives us allows us to express the same concepts in much less space. So having lighter code bases means there's a lot less investment in them, which makes it easy to scrap and rebuild should it come to that, as opposed to something like Java, where the code base is just so much more verbose, there's much more volume to it, and volume translates to inertia. So that's it for the manifesto part. Massive has been around for several years. It was originally Rob Connery's project, one of his micro ORMs. He started that in 2012. I began contributing to it in 2015, and eventually when Rob moved on to become a hipster and do Elixir stuff, took over the project. Massive is what I would call moderately popular. The clear heavyweight in terms of data access with Node is Mongoose, which is an ORM for MongoDB. We're a couple orders of magnitude less popular than that. In terms of relational data, the household name, if you will, is SQLize, which is, again, much more popular, but in sort of the second tier of data access frameworks, Massive is a small but contender in there. I expect that the Postgres-exclusivity probably accounts for some of that because a lot of people still do have to use MySQL or SQL Server. But the fundamental approach that Massive takes is that MongoDB really got the whole JavaScript as query language thing correct. So in the spirit of good artists copying, we're just going to steal that and run with it. So the database isn't just a black box that you push information into and pull it out of. It's an active principle in whatever system it is that we're building, and we need to respect it and use the metaphors that we already have for interacting with principles like that. And that's the application programming interface, or API. So Massive connects, given information that you pass to it, and returns an instance that has objects attached for your tables and views and so forth, and just provides an idiomatic interface for interacting with those database objects as objects. One of the most frustrating things about working with an ORM is having to first define and later maintain models. That's not happening. For us, we talk directly to tables, to views, and to functions. It follows more of a process of translation instead of reimagining your data model as an object model. So this allows direct usage of just about the full feature set of the database. So you can use functions, which other data access frameworks often ignore. You can use triggers without having to worry about what it's going to do to state, and triggers are fine. I believe it. And it's better for command query responsibility segregation too, because you don't have three data models. You can just talk directly to your tables to persist data and to your views to actually read it. If we have these things actually attached to a connected instance, we need to represent what goes on inside each database object. So the first aspect of these building blocks is whatever you can issue a select statement against. Each of these methods invokes one of the four SQL statement generators and returns a promise for results, which generally is an array of records. Exception there is find one, which obviously returns a single record. Count returns a number. Find one and count are taking a criteria object. Although find one there has a primary key, you can switch them out. The criteria object allows you to generate conditions to look for records in the table or view. So it just ands together predicate key value pairs that you pass it. We do allow both JSON traversal in a much nicer format than Postgres would otherwise have you doing it, and operations. So we can look for artists who started exhibiting before 1900 without having to do anything too complicated. If you need to write more complex conditions, you can also use an OR key and pass an array of other criteria objects, and it will take care of the rest for you. So this covers a lot of your basic criteria use cases. There is actually another readable method that lets you handwrite a SQL-style where clause or prepared statement-style where clause. I have built 2 enterprise applications on top of Massive, and I have not had to use it once. So it's there mostly for backwards compatibility at this point. Secondary to readables, you have the writables, which are things that you can push information into. When we're pulling these things out of the database and building the API, we actually apply prototypes on top of each other to allow something that can be read from and written to be consistent with things that can only be read from. Save here is sort of a one-size-fits-all, put this thing back in the database. If you pass it a record that includes a primary key, it's an update. Otherwise, it's creating a new one with an insert. So this is not a true Postgres insert with the on-conflict clause. Instead, Massive knows what your primary keys are and determines which statement to emit. You can also skip the magic and go directly to insert or update. Update here is doing a bulk operation. It takes a criteria object or primary key and then a map of changes to apply to matching records. Finally, destroy, because delete is a reserved word in JavaScript and we can't even use it for a function name. It does what you think it does. It removes information. It can also take a criteria object or primary key. Last but not least, and the correspondence with Unix directory permissions is fortuitous, you have things that you can execute. This includes both database functions and SQL script files, which Massive loads up on initialization. It treats them as identically as possible, although there are a couple of fundamental differences. First, that you can nest files under multiple levels of folder. Second, that we can optionally make function execution a little bit nicer by detecting the output shape. So if it only returns a scalar value or a single record, we can do that instead of the usual list of result objects. Having scripts is actually pretty great because it allows you to work in files first, which are a lot easier to modify than database functions. And then once things are stable, and if you feel like it, you can bake that into your database formally. Or you can just leave it as scripts. Nobody's going to judge. Using transactions or using the API with transactions has been one of the most requested features over the years, and it's finally part of version 5. The canonical example for database transactions is moving money between bank accounts, but that's boring. So instead, in 1915, Kazimir Malevich, who's a prominent constructivist painter, broke decisively with that school at the 010 exhibition when he showcased his first works in the new suprematist style that he'd come up with. He had actually covered the windows of his workshop with newspaper, wouldn't talk about art with just about anybody for months and months before the big reveal, which is surprisingly analogous to working inside a transactional context. You do a bunch of work in isolation, then finally either commit and it's visible to everybody else, or you roll it back and nothing ever happened, we swear. So with the with transaction method, you get back a copy of the connected instance and can start issuing API methods against that work inside that transactional context. So we can go out and find Casimir, create his new movement, destroy his links with all other artistic movements, and finally return a promise that will create the link between Malevich and suprematism. When that last promise resolves, the transaction is committed. If at any point there's an error thrown, everything's rolled back. So having these building blocks is great, but of course we need to know how to actually, or what actually to build. So to do that, we have to ask the database what's inside it. The ANSI Standard defines a information schema that contains basic metadata for your database. Here we're looking at 4 tables. Tables obviously contains information about the tables that exist in the database. We look at columns to figure out what's actually inside them, at constraints to see what the primary keys are. It also includes foreign key information, but we don't use that. And finally, key column usage correlates columns and constraints. So it tells you which columns make up which constraints. So there's actually dozens of entries in the information schema, but these are what we're interested in for our purposes. For the rest, we have to dig a little bit deeper. Postgres actually implements the information schema as a set of views on these system catalogs. Again, there are many, many more, but the ones we're interested in, PG namespace corresponds to the schema or schemas in your database. We need the OID to track certain other internals. PG class corresponds to the information schema tables, but again, we need the OID because table inheritance is the thing, and we need to know which tables extend which other tables' schemas. We did not use the information schema to look for information about views because the information schema is not defined as tracking materialized views, which are a separate set of view that actually saves its results as kind of a cache. And we want to include both of them and do it as consistently as possible, so we just go directly to the system catalog and pull that out. We also have to use PG attribute to find columns in views because those are not defined in the information schema again. So if you look for information schema columns belonging to views, you'll come up empty. We also use the PG relation is updatable function to determine whether a view can actually be persisted to. If you meet certain criteria, such as only querying a single table and not doing any aggregation, you can actually insert, update, or delete to a view, which is pretty neat. Finally, pgproc contains information about functions. There is an information schema routines table, but it doesn't give us enough information. We need to know what the results look like and number of arguments, whether it's a variadic function that can take an arbitrary number of arguments. And that all goes into both the invocation of functions and sort of the enhancement that Massive offers to unwrap results where possible. Last but not least, we look at the file system. If you use Massive in a Node project, you can have a database folder or a DB folder, or rename it as you like, and change your configuration on connection. And Massive loads those up as closely to functions as it can. I do have to give some props to Vitaly Tomilov, the developer of the pgpromise driver that Massive uses under the hood. It also uses his query file parser, which enables a lot of pretty cool stuff. So you're not limited to just working with prepared statements with numeric placeholders. You can use named parameters. You can interpolate column and table names and do some really cool dynamic stuff with that. But there's one potential problem with having multiple sources of database and other objects, which is, what do you do when names collide? Here we've got an auth schema, an auth folder, a groups table, and a groups folder with a SQL script in it, then a users table, and a script which will eventually become a function named users. So this is where prototypal inheritance really saves us, because if we were working in a class-based inheritance model, we might not be able to actually resolve this. But with prototypal inheritance, as we load new information, we just keep applying prototypes on top of whatever we have. So when all is said and done, we'll have a single auth object, although that was always just a namespace. We'll have a groups table with find, insert, update, and so on. That will also contain a permissions function that you can invoke directly. Users, again, will be a table with the usual set of methods, but it will also be a function that you can just go ahead and invoke and not worry about whatever else is on it. There are two cases that we can't handle with this. One is when you would collide with a method on a readable or writable. So if that groups folder were to have a find1.sql script in it, that would overlap the table find1, and there's nothing we can do about that. If the second case is if you have a script and function that resolve to the same name at the same path, again, we can't have the same function do two different things. So in both cases, we just abort and raise an error. So as long as you spin Massive up before you roll out to prod, you're good. Having readables, writables, and executables gives us basic feature parity with ORMs at really a fraction of the price. There's no models to maintain. There's barely any state management, and it's totally optional with save. There are a few gaps, though. There's nothing yet about shaping query results or modifying their behavior, and there's nothing about working with related objects, which is really a strength of a parallel data model where you can build up an object graph and flip it over into the relational graph. First off, being able to affect what queries do or how they do it. Here we're looking for artists with the criteria object, but just about every API method can take as a final argument options object, which is a little bit of a kitchen sink that tells the engine to do something different. So here we're looking for only 2 fields. Everything else is excluded from the results that come back. And we're sorting with the order option there. These on the right are a subset of the available options. Build does a dry run and actually returns the SQL that would have been emitted. Fields and expers modify the select list. Expers is unsafely interpolated. Do not pass user input directly to it because you will get SQL injected. But if you have to do some arithmetic or call a function on a column, that's how you do that. Offset, limit, and order do the slicing and dicing that you expect they do. Only is used with persistence methods for tables which are inherited by others. In Postgres, by default, if you update a parent table, the update will actually cascade out to the children, but you can set only to turn that behavior off. On-conflict ignore is used with insert and allows you to insert something with a primary key without worrying about an error if it already exists. Finally, single returns only the first result, and stream returns the entire result set as a node stream so you can work with it over time. As for object graphs, or complex sets of related objects, the first sort of piece to that is turning tabular results like this into something a little bit more friendly. So if we have a view that joins tables together, that means there's probably going to be duplication, because you have the same information appearing once for every corresponding record. Getting that, or something that looks like that in SQL is perfectly all right, because SQL is built to work with sets. In JavaScript, though, we'd rather iterate and traverse. So the way we do that, I kind of lied about models. We have to have the developer actually tell Massive what the expected result should look like, because we have to handle arbitrary cases, and they can get extremely complicated. We can't rely on something like column nomenclature, where you could token out aliases in views or something, because view might not have it, and it may not be possible to change that. So you define a schema that says the root record is defined by such and such primary key. It has these columns attached to it, and every other thing is a descendant record or records. So each of those has its own primary key, its own columns, which can be renamed, and is either an array or a single object. So it's a little bit complicated, it's a little bit crappy, but the payoff is that you just have to pass it in when you need it and not otherwise, and you get back exactly what you need. So a list of movements, where each movement contains a list of artists, is much more amenable to processing in JavaScript and much less crappy to deal with than trying to figure out if you have everything in order and keeping track of pointers within nested arrays. So this does not actually give us a full object graph. It's a hierarchy, and it can only ever be a hierarchy. But we're not trying to go toe-to-toe with ORMs on this subject. We're trying to be as convenient as possible and then get out of the way. So having this as an optional addition for when you really want to do some complex results processing, and only when you want to do that, makes it easy enough without having to build up all that overhead that you would need to do this on a full scale. It also avoids a common trap with data access, which is the n+1 select problem, where if you approach this problem from the start, you would think, okay, let's go out and get all the movements and start iterating over those. And you go out and you find all the constructivists, all the suprematists, and so on and so forth. And by the time you're done, you've issued as many queries and made as many round trips to the database as you have movements, plus the original query to get the list of movements in the first place. So because we're working with a single query, that doesn't enter into the equation at all. The other side of working with related objects is, of course, persistence. So it's a common use case that you have a many-to-many relationship set up, and one side of it is already populated. You want to add an entity to the other side and set up the relationship, ideally in the same transaction, so nobody sees the partial state of the database. So here, if we have a movement defined and we want to add an artist to it, we can do that. The JavaScript side on the left there is at least simple. The SQL is not. But if you turn the deep insert option on, you can pass an object to insert where any key that is not recognized as a column defines a junction. So our junction table is named movement artists. We want to add a link to movement number 5. Because we haven't actually inserted Ivan Kliunkov yet, artist ID is undefined in the JavaScript. So that eventually turns into that mess of SQL on the right, where we use probably my favorite Postgres feature, which is the writable common table expression, to insert the original record that we wanted to insert, and then return everything that we affected. So returning allows you to sort of treat persistent statements as read statements, which is immensely powerful. In other databases, you're usually limited to selecting at identity or using the scope identity function or something like that. With Postgres, you can just get back whatever you just did. So we take that and we set up a second CTE to actually create the link. And that generates an insert select, which uses the inserted record to actually populate that formerly undefined artist ID. And finally, for consistency with the other uses of insert, we just return the original record because that's what you would expect to get back out of there. So this does only work for unary inserts because managing location would be prohibitively complicated with an array of records coming in, but it does allow multiple junctions and multiple records in each junction. So that's enough about ORMs for now. Let's switch gears a little bit and eat MongoDB's lunch for a change. Relational databases are traditionally terrible at working with hierarchical data. If you've worked with them for long enough, you've probably seen a table that has a parent ID column and a self-joining foreign key, or you might have seen somebody try to decompose a complicated structure across a dozen or more tables. I've seen both. It's horrifying. But Postgres offers really robust JSON support, and that means that we can take advantage of it to sort of do something similar to a MongoDB collection inside a relational context. So it makes it much, much easier to work with complex or hierarchical information without having to switch things around too much. SaveDoc is just a method on the connected instance itself. You can pass it a collection name and a document to initialize it with, and it will persist it and return the new document record. So looking at that, because it is a row in a table, it has a primary key. When you pull a document out of the database through the document API, it attaches the primary key automatically. When you persist it back, it removes it. So you're never storing a redundant primary key. It's handled automatically behind the scenes. There are some metadata fields with a trigger that updates the updated at. There's a text search vector, which includes the values present in the document body. So this all allows blending document and relational strategies, or even using documents for rapid prototyping. If you have the general layout settled, but you don't know exactly what columns you're looking at defining, you can use the looser schema of a document collection and then transition to a proper relational schema on your own time without having to switch databases or integrate a second data store, which would actually prevent you from having referential integrity between your sources of information. So there is a document API. FindDoc works exactly like the tabular find in that it takes a criteria object. SaveDoc is a little bit different. It's all or nothing persistence. So it will completely replace the document body if it exists, otherwise it'll create it, and of course nothing was there before. If you want to merge in new information without having the full document up front or ahead of time, you can use update doc, which, like the tabular update, can take either a criteria object like it's doing here, or a primary key. Finally, search doc works exactly like the readable search in that it does a full text search on the body. I do have one cautionary tale about all this, though, which is that delete with criteria is extremely powerful, but oh boy, is it dangerous. So the applications that I developed on top of Massive were accessibility testing suites. The idea was you would have your testers go out, look at websites, discover issues, report them in the web app, and keep on going. So we decided at some point that it would be really nice to be able to manage the issues that people were finding in bulk. So went through design, went through development. The developer who actually implemented the bulk delete side of this missed a very important step, and then I missed a more important one by passing it through code review without realizing something was up. So we deployed, and about a week later, somebody noticed, hey, cool new feature, and promptly dumped the biggest table in production. So we had to go to backups for that, which was not very much fun. So the moral of the story is, if you're using criteria with destroy, make sure the criteria actually reach it. So every decision in software development builds on what's underneath it. When you pick a tool, you're not just selecting a library or something that adds a little bit of functionality. You're choosing a model of a way of thinking. And different models and different thought processes are more appropriate for different situations. Your choice of database is as important as any other choice you're going to make, if not more, and there's no opting out. You can't say, we're just not going to think about the database, because that is in itself a statement about how you feel about your database. When you have a data storage problem, it's relational unless and until you can articulate otherwise. But even within the domain of relational databases, there are some really clear differences, and I think Postgres makes a very strong case for being the best product available on the market right now. Focusing on Postgres exclusively is what makes Massive a powerful library. Close integration is something to be very judicious about. It's not appropriate for all requirements, but if you can commit to doing that, it is 100% worth it, especially in something like JavaScript, which allows you to write much leaner APIs that rely on SQL for the really complex operations, and just use whatever affords more convenience in the day-to-day or simpler stuff. Software development just goes a lot faster when you have the full toolkit that Postgres has to offer at your disposal. If you treat the database as just that dumb black box that you push things into and pull them out of without thinking about them, that means that you have to put in a lot of effort to reproduce the utility that it wants to give you for free. So the evolution of data storage with everything that we've been seeing coming out is really exciting, but we also need to think about how we actually work with the databases that we have. So there's a lot of room between the raw SQL statements and the overweight abstractions that ORMs give you. Data mapping kind of threads the needle there, and it and the API approach have proven really efficient for agile development in JavaScript, even more than they do in more formal languages. So I hope you'll check Massive out, but even more than that, I hope you'll go back and think critically about what you're actually doing with your database and use the appropriate tools and abstractions for whatever it is you're facing. That's it.